Welcome back, guys, to another episode of Tumor Teaches. Today, we're going to be going over stoichiometry and um, sort of how to do the problems and sort of how it works. I do warn you that this is probably going to be a fairly long video to the tune of half an hour, so sit tight and yeah, let's just get into it. So, balanced chemical equations often contain stoichiometric numbers that express. Well, first off, I should probably go define what a balanced chemical equation is. So let me quickly pull up that set of notes here. Uh, should be something here with to do with balanced chemical equations. I think it's here. Yes, it's here. Okay, so first off, let's even start with a chemical. What is a chemical equation? It's an equation that describes a chemical reaction. So we generally have reactants turning into products, which the arrow can be verbalized as forms, yields, produces, or goes to, or whatever. Equations must be balanced, and the way you balance them is you cannot change these molecular formulas here. However, you can change what are called the stoichiometric numbers or the stoichiometric coefficients. Same thing. Um, these numbers here up front. So, for example, let's do so for example here, let's do an example here of the combustion of methane. So on my screen here, we'll have a blank here, H4 plus O2, which goes to CO back here. Eraser. God damn it, it's so hard to. Alright, let's. So let's do an example of balancing an equation here. It's a pretty simple process. Um, so here we have the combustion of methane. So we look here, start with any element, it doesn't matter. However, one trick I would like to always give is that these lone elements here, save them here to last because they tend to not affect the whole equation. So here for hydrogen, let's do a little chart here. So CHO PR. So let's pick with hydrogen here. So on the uh, whoops, I should probably switch these around. My bad. I should probably put some more planning into these lessons, but that's regardless. RP. That's a really bad P. There we go. So for hydrogen here, we have 4 on the reactant side. Remember, this is the reactants, anything to the left of the arrow. And on the product side, we have currently, since there are blanks here, we just assume them to be 1. So we have 2 here, which that's obviously not balanced. So let's slap a 2 here to make that work. And then now we have 4. Um, but and now that we have oxygens here, now is a good time just to make sure that those oxygens are balanced. So we have 2. We have 2 from this water, and then we have 2 in the uh, oxygen here. So 2 plus 2 is 4, and we currently have 2 here. This subscript here says we only have 2 atoms of oxygen, so that's not balanced. However, I'm going to wait to balance that just in case it balances out with something else. Now lastly, let's consider carbon. There's 1 atom here, 1 atom here, so that's fine. So let's just put a 2 there, and then I like to put in the 1s there. So that is our balanced reaction. So when you count atoms, just remember you cannot change these subscripts. However, you must count them when you do it. So for example, when you count for the number of atoms, you do these stoichiometric coefficients here times these times this here, and basically, as part of the law of conservation of mass, you cannot change the number of atoms that are on each side. The number of each individual atom must stay the same throughout on both sides in order to make sure that the law of conservation of mass is not violated. So that's the reason why we do that. So Now that we know sort of what a balanced chemical equation is, let's move forward here to talk about stoichiometry. Stoichiometry is just sort of the study of sort of these. It's just sort of the study of if I give this much product, what will I yield? So, um, based off that little balance. So sometimes you'll be asked to balance the chemical reactions first, and then once you've done that, now you'll be given in the next part of the question. They'll say, okay, given say you had 12 grams of oxygen, how many grams of CO2 would you yield for that combustion reaction example? So they at the very core they can be applied to molecules or formula units. Think of this as sort of like a recipe book, if you will. If you have, and at the end of the day, you need to be comparing what is essentially molecules. And how do we do that? Well, we can either compare just straight up the number of molecules. So here, this reaction tells us that for every one atom of oxygen here, we need to have two atoms of hydrogen. No, or every molecule of oxygen, we need two molecules of hydrogen. So they need to be in a 2-to-1 ratio. And we do happen to have that. So here we have two oxygen atoms, two oxygen molecules, and here we have four. And then that makes two oxygen, not two water molecules. So it's in a 2-to-1 to 2 ratio. And then, so that's sort of that. And dealing with this at molecules, it's the easiest way to do it, and it makes sense intuitively. Less obvious is that what we always want to do when we do stoichiometry is we always want to work with moles, because remember, a mole is just 6.822 times 10 to the 23 atoms. So if you had let's forget this set of mole here for a second and say if we had 2 dozen oxygen atoms, we would need 4 dozen hydrogen atoms to make 2 dozens of 2 dozen water molecules. Hopefully that should make intuitive sense to you. And then if we again just remember that the mole is just 6.02 times 10 to the 23. It's R akin to the dozen. If we have 1.8 moles here, we would need 3.6 moles here, exactly double this one, to get 3.6 moles of water molecules, which is exactly double this one. Note here that 3.6 to 1.8 to 3.6 is in a 2-to-1 to 2 ratio. And then here we have how many. So the key to stoichiometry is work in moles. If you work in moles, your life will just work in moles. It's easy to do, and that's the way you do this. You can just use dimensional analysis to get. You always want to work with moles of stuff. You never want to work in grams. You never want to work in concentrations. When we go to gas laws later on, you'll see that sometimes you'll have no choice and you'll have to work with those numbers. But if you can, work in moles. It makes your life really easy. So, lastly, before I go on to do a couple of sample problems, theoretical yield is the amount of product you expect to get, and then actual yield is what you actually get in the lab, and then percent yield is just what percentage of the theoretical yield did you actually achieve in the lab. Um, it's actually called experimental yield, but same idea. Then lastly, we have to go on to talk about the idea of a limiting and an excess reagent. Um, you can think of the limiting reagent as sort of the bottleneck of the process. It's the thing that's causing the reaction to stop early. So the limiting reagent is the reagent that is totally consumed in a reaction, and there should be none of it left by the time the reaction's over. And the excess reagent is the thing that's not totally consumed. The only thing I should warn you here is that you always want to do your math with the limiting reagent, because again, it's the bottleneck. So if you have a bottleneck, you can only go as far as the bottleneck sort of allows you to go. So, for example, here in this one, we know that we need a 2-to-1 ratio of oxygen atoms. So in order to do that, since we have 7 moles of hydrogen atoms here, if we want to get this 2-to-1 ratio to work, we would need 3.5 moles of oxygen atoms here. 3.5 molecules, whatever. You get my point. You need 3.5 of them. However, since you only have 3 here, this is sort of bottlenecking the reaction, if you will, and therefore it only uses 3. All 3 moles of that is used up, and therefore when the reaction's over, we still have a mole left. So that means that oxygen is the limiting reagent because that's the one that caused the reaction to stop it's the bottleneck, and then hydrogen is the excess reagent since there's still plenty of it left after the reaction's over. So let's sort of do some sample problems. Um, Lastly, too, before we actually go on to do the sample problems, the last thing I want to talk about here is just quickly about solutions, because you're going to be working with them quite often. A solution is nothing more than a homogeneous mixture. The solute is the thing that you dissolve in, and the solvent is the thing. No, the solute is the thing you're dissolving, and the solvent is the thing you're dissolving it in. So, often a liquid and often a solid. Soluble describes if something can dissolve. Miscible something is an adjective that'll describe if something mixes in. When we talk about quantities of chemicals in solution, we talk about the concentration, how much quantity of the solute is over the solution. And the most common units you'll use in the lab are molarity and ppm, parts per million. Um, so here are some verbs. Dilute is an adjective and a verb. It's just meaning low concentration or making things of low concentration. And concentrated, again, adjective or verb, depending on the context, which just means high concentration or increasing the concentration. And a standard solution is a solution which you know the concentration of. So molarity is just the amount of moles per the volume of solution. So, and you say it verbally as molar, and you can often abbreviate it to this big capital M. The only thing to note here is that when you do these concentrations, these ionic compounds, when we go into in topic 4, will dissociate fully. So therefore, you will have 2 moles of chlorine ions in the solution since they dissolve and break away. So you'll have 2 times whatever the concentration is of the salt. So let's go ahead and now do maybe 1 or 2 sample problems. So let's do a sample problem here. How long have I been going on? 12 minutes. I knew this is going to be long. So a sealed glass container is emptied out and used a vacuum pump. Right? And propane gas is ignited. The question is asking us here, what are the masses of the one remaining product and what are the masses of the reactant, any remaining reactant, and the products when the reaction is done? So firstly, I think it would be a good idea to just get a balanced equation here. H8 plus O2, which goes to so let's quickly balance this one. So there's 3 here. I need, okay, that's not gonna work. So if I put a 2 here, now if I put a 4 here, 4 plus 6 is 10, so that's 5, 1. So, okay, now that that's balanced, what I like to do generally when I do these problems is first I make a chart. What I do is make a chart like this. This is before and after. So we are told we start with 85 grams, which if I put it through a conversion factor, equals, and I'm also told we have 315.27 grams. And every 315.27 grams per. So the first thing I like to do is, with the things I have, I convert everything into moles. So this would require pulling out a calculator. So I'll pull up the calculator so you can see what I'm doing. So x2 divided by, so there are 3 plus 8 times 1.0794. When you do enough of these, you'll eventually have the numbers memorized. So 336 plus 8. That sounds about right. So we would have, according to this, we would have 1.94 mole. And then for the oxygen one, so 315.27 divided by 31.9988. And that one yields us 9.85 mole. So in order to figure out the number of moles of fuel we use, now we have to decide what the limiting reagent is. Usually it's quite obvious what it is. However, what it's not, what you can do is you could take the number of moles of the substance you have initially and divide it through by the stoichiometric number. So if we divide this through by 5 in this case, so I would divide this through by 5 and divide this through by 1, and we get 1.94 compared to 1.97. So therefore, this is the limiting reagent by doing that process. I don't know why that works, but it does work. So if you ever in a pinch, divide the number of moles of the substance you do have. So in this case, it would be 9.85 divided by 5, and you'll get sort of the number of grams where you have per like stoichiometric number, and the one with the lowest, and the one that when you do that process with every element, every substance that partakes in the reaction, the one that yields the lowest result is the limiting reagent always. So that's sort of how I do it systematically. So now that I know that, I'm going to put a little L next to this, and I'm also going to put that as 0. Now, since I know that there's 5, since I know that they're in a 5-to-1 ratio, I can write this out as a conversion factor here. Or alternatively, what I can do is, since I know this is 5 and this is 1, I can just multiply by 5 over 1. So in that case, that's just the stoichiometric number of this one over this one, and generally it's just the stoichiometric number of what you have, what you want over what you have. So if I were to multiply this by 5, we would get the number of, so 9.85 subtract 5 times 1.94, and that would give us the moles of remaining gas, the moles of propane that remain. So just quickly, so what I do is 9.85 subtract 5 times 1.94, and that yields us with 0.15 moles of oxygen remaining after the reaction. And then for the CO2, we remember, since this is the limiting reagent, we must do all our math based off this. This is 3, this is 1, so we multiply by times 3 over 1, which yields us here 1. My God. What is it with these headphones? I swear. They're Bluetooth headphones, so if they're not used in a while, they don't tend to like me. So what I'm going to do is I'm not going to use them with Bluetooth. I'm going to use them via an aux cord, if you will. One of the aux cord. Yeah. Alright, now that my audio has been fixed, hopefully permanently, at least for the remainder of today. So, as we can see here, we multiply by 3 over 1, which yields us which yields us 5.82 moles. And then lastly for H2O, again, it's just simply, since that's 4 here, it's 1 here, it's in a 4-to-1 ratio, we want to quadruple it. So times 4 over 1, which yields us 7.8 moles, 7.76 moles, 7.76 moles. And that's more or less the idea. Key takeaways is that always first write your balanced equation, then convert everything into moles from whatever you have. You can just use dimensional analysis to do it, or what I call conversion factors, or you can memorize the formulas, or however you get there, just get there. And then remember that it's just ratios, so if it's in a so alternatively, another method that works for some students is that 5 to 1, and then you have it's in a 5 to 1 ratio, x to, since this is a limiting reagent, it would be 1.94, and then if you keep that ratio up, so you multiply that by, you also want to multiply this by 1.94 to get the moles of oxygen that was used up. That's sort of how that works. And then with solutions, it's just, you can always do N equals C times V, which is concentration times volume. It's pretty simple stuff. Rather than me let this go on for 30 minutes, I'm going to stop it here. And what I might just do is I might just end up making a companion video to this one, going over a couple of these problems. But hopefully that's just enough to get the gist of it. Thank you again very much.